Everyone have their notes? Okay, get them open. We're going to jump right in. So for a function f of x, the reciprocal would be 1 over f of x because we flip it. If you think of f of x, it's all over 1. If you flip that, it's 1 over f of x. Okay? Where f of x does not equal 0. Okay? So why can't f of x equal 0? Why can't f of x equal 0? You can't divide by 0, right? So the y value, f of x is another word for y. Y can't be equal to 0. Okay? So let's write do you remember MPVs from rational expressions? What x can't be? So in this first one, what can't x be? 0, because then you would be dividing by 0. Okay, this guy. Does it have any MPVs? No MPVs. Right. 1 over x plus 2. X can't be negative 2, because then that would make the denominator 0. And what would I have to do with this guy? Factor. Good. Two numbers that multiply to positive 4 but add to negative 5. Negative 1 and negative 4. So x can't be equal to 1 and 4. Opposite signs. Okay. So what's the reciprocal of 4? What would be the reciprocal of 4? You flipped it. 1 over 4, right? The denominator, if you don't see it, is 1. So you flip it, 1 over 4. Okay, what's the reciprocal of a half? 2 over 1 or 2? Right? 2 divided by 1 is just 2. So 2 over 1, which equals 2. The reciprocal of x would be 1 over x. And the reciprocal of f of x, 1 over f of x. Okay, so we're going to start with the most basic equation you can possibly think of. And that's y equals x. Or f of x equals x. Y equals x. That's simplest equation. So if we're graphing y equals x, if x is negative 5, what's y? Think of the equation y equals x. If they're equal to each other, negative 5. If x is negative 2, y is negative 2. If x is negative 1, y is negative 1. Okay? So y is equal to x. They're the same thing. The most basic linear equation known to man. Okay, we're going to graph that. So y is x. Y equals x. So let's plot those points. 0, 0, 1, 1, negative 1 and 1, negative 2 and 2, negative 5 and 5. Would be here. Positive 5 and 5. If you have different colors, or if you have highlighters today, it's going to be really helpful. Or like different colored pens, or a pen and a pencil. Very helpful. Okay? So that you can actually distinguish between your reciprocal graph and the linear graph. So we're just going to practice graphing linear equations. Think about this graph compared to grade 10 when you studied mx plus b. Okay? When you studied mx plus b, what's the slope of y equals x? If you don't see a number in front of the x, what's the coefficient? 1. What's the y-intercept if you don't have anything being added? No, 0. 0. The y-intercept is 0. Right? So looking at this, you can see the y-intercept is 0. And the slope is positive 1. So let's draw that line. You might want to use dotted line. Well, no, not a dotted line, actually. Okay, so we're going to graph the reciprocal of this. And this is where it's going to get fun. Okay, so let's think about the equation y equals 1 over x. So 1 over f of x, or f of x is just x, y equals x, right? So we're going to graph 1 over x. And we'll look at that on our calculator after. So if x is negative 5, the reciprocal of that would be 1 over negative 5, or negative 1/5, or negative 0.2. Okay, if x is negative 2, what's the reciprocal of that? I'll make it really large so you can just do the table of values first, and then I'll take away the zoom. So negative 1 over 2, or negative 0.5. Reciprocal of negative 1. What's the reciprocal of negative 1? Negative 1. 1 special, because when you take the reciprocal of it, it's itself. It's already over 1. Yay. Okay, what's the reciprocal of negative 0.5? Negative 2, good. Reciprocal, because this was the same thing as negative 1/2, right? What's the reciprocal of negative 0.2? Negative what? Negative 5, because this is the same thing as negative 1/5. Reciprocal of negative 0.1. What is negative 0.1 as a fraction? Negative 1 over what? 10. So the reciprocal of that? Negative 10. Reciprocal of 0. No, not 0. Nope. Why is it undefined? Because it becomes 1 over 0. Can you divide by 0? No. Undefined. Reciprocal of 0.1. 10. Reciprocal of 0.2. You can see the pattern. 5. Reciprocal of 0.5 was 2. Reciprocal of 1. 1. Reciprocal of 2. Half. And a reciprocal of 5 is 1/5, 4.2. Okay, so we're actually going to plot these. I want to point out 2 things really quickly. And that is, I'm just going to highlight them. When x was 1, or sorry, when y was 1. So these points here are called our invariant points, because when we took the reciprocal of them, right, do you see how if you compare the y values, negative 5 became negative 1/5. Negative 2 became negative 1/2. Negative 1 is still negative 1. When we take the reciprocal of the y values, those ones never change. So when our y values are 1 or negative 1, they're not going to change. If you look at the original function compared to the reciprocal functions, these points are still the same. Right? Those are the exact same coordinates. These are what we call invariant points. Invariant. Invariant points stay the same. We'll talk more about that later. Okay, so we took these points of x and y, x comma y, and they became x comma 1 over y. When we took the reciprocal. Notice the x coordinates stay the same, but we're just taking the reciprocal of the y coordinate to get these new coordinates. Okay, let's graph these points. So I'd like you to take these points here. If you have a different color, that would be great. And try and plot as many as you can of these guys, these coordinates. Some of them are a little tougher to plot, but they're doable. Okay, so I'm going to do in blue. So for example, negative 5, when x is negative 5, y is negative 0.2. So it's really close to the x-axis there. You're estimating a little bit. Okay. When x is negative 2, y is negative half. When x is negative 1, y is negative 1. Notice this is where the point didn't change, so it's the intersection point of the reciprocal and the original graph. When x is negative a half, y is negative 2. So something like there. When x is negative 0.2, it's negative 5. Right there. We can't do the 10. That's okay. Okay, so the graph actually looks like something like this. We already talked about how y can't be equal 0. Okay, so this is 1/2 of the graph. So 1/2 of the graph is going to look like this. Okay? Connect those points. We're not going to cross the x-axis. Don't cross the y-axis. We're going to approach it but not cross it. And we'll talk about y in a second. Okay, now graph the other side. So when x was 0, y is undefined. We'll talk about what that is in a second. Leave that for now. 0.1 is 10, that's too hard. 0.2 is positive 5. So up there. 0.5 is 2. So half is 2. When x is a half, y is 2. 1 is 1, so there's my invariant point. 2 is a half. And 5 is 0.2. Okay, so there's the other side. So if you grab your graphing calculators, we're going to talk about some of these features, but let's take a look at what your how it looks on your graphing calculator. Okay, so go to y equals, clear what's there. And let's graph 1 over x. We're just going to graph the reciprocal. If you wanted to go y equals x, you can, but we really want to look at that reciprocal, 1 over x. Oops. I wonder if there's a way. No. Hey, put that away. Okay, go to graph. Now, some of you have older some of you will have older calculators, so your calculator might draw a vertical line in. Zoom 6 if your windows are weird. They might be. Zoom 6. Or we might want to change it from -5 to 5, like what we have there. So this is what it looks like. Okay? Does anyone have a vertical line kind of being drawn here on an older version? Can't really tell, I guess, because that's where the axis is. You'll be able to see in a few more when we do a more complex graph, but sometimes your calculator will try and connect these 2 points. And so it'll draw a vertical line, which it shouldn't be drawing. Okay? So where we originally had an x-intercept, our x-intercept originally is when y is 0. Right? Can you take the reciprocal of 0? No, it's undefined. And so at the original x-intercept, we're always going to have something called an asymptote. And so we want to draw that vertical line in here. This is an asymptote. Okay? That's going to be an asymptote. Gotta love that word. So an asymptote is, in Math 20-1, because I want to be very careful how I word this, it's a little different in calculus, but an asymptote is a line you never cross. Okay? A vertical asymptote you for sure never cross, ever in math. So there's different types of asymptotes. You can have a vertical asymptote, you can have a horizontal asymptote, you can even have a slant asymptote. So it's essentially a line that the graph doesn't cross. It's going to approach. It gets closer and closer to, but never touches. Okay, because you can't take the reciprocal of 0. What happens when you take the reciprocal of a large number? What does it become? By the large number, like, let's give me a large number. 200. Okay, what's the reciprocal of 200? 1 over 200. It's really close to what? 0, right? So if the reciprocal of a really large negative number is going to get closer and closer to 0. It's still negative. Reciprocal of a negative is still a negative. But it's approaching that 0. What happens when you take the reciprocal of a small, small, small number? Like 0.01. What is the reciprocal of 0.01? What is 0.01? Same thing as 1 over what? Yeah, this is the 100th place value. So what's the reciprocal of that? 100. So what happens when you take the reciprocal of a really tiny number? It gets really large. It's going to get really large. So the opposite happens because we're flipping it. So if it's a really large number, the reciprocal is really small. If it's a really small number, the reciprocal is really large. Okay, so the y values here are really, really tiny. When I take the reciprocal, guess what happens? They're large. These y values are really, really small. Oops, these ones are really, really large, these y values. When I take the reciprocal, they become small. Okay? So there's two asymptotes here. Do you see the other asymptote? So one is at x equals 0, the vertical line. I should use a highlighter because it's hard to tell. So this is, and you always want a dotted line, okay? Never a straight line, a dotted line. So there's one asymptote. Where's the other asymptote? On the x-axis, yeah. So you're going to have one at y equals 0. So that's the horizontal asymptote. So horizontal asymptote. And that one will always be there. And then the vertical asymptote will always be where the original x-intercept was. Vertical asymptote, x equals 0. Okay? And notice your invariant points are always going to be the points of intersection. And that always occurs when y is equal to 1 or negative 1. Okay? So those invariant points are when y is equal to plus or minus 1. Because if you take the reciprocal of 1, it's still 1. If you take the reciprocal of negative 1, it's still negative 1. Those are your invariant points. Those are the points of the intersection of the original graph with the reciprocal. Okay? Hot IT. So I like to always say, like, you can't touch my asymptote. It's a good way to remember it. Right? You can't. You'll get in trouble. Very big trouble. Not appropriate. Very not appropriate. You can't touch my asymptote. So it's a line you approach but never touch. Just don't touch it. Okay, notice that the y value is changing in the reciprocal of the function. So we talked about that. If I had a point of 5, 5, when we take the reciprocal, it becomes 5, 1/5. That's a great multiple choice question. Okay, so we only take the reciprocal of the y value. Invariant points are when y, where are the invariant points on this graph? 1, 1, and the other one was negative 1 and negative 1. And this happens when our y values are 1 and negative 1. Okay, so when y is equal to 1 or y is equal to negative 1. The x's might be different. Because when we take the reciprocal of that, it's still the same number. Okay. So we're going to fly through like this next part on asymptotes. We kind of talked a bunch about them already, but I'll just key into some key information here. It's a lot of reading. So what you can do tonight, some light reading. Okay. A rational function is defined for all real numbers, except for those which make the denominator 0. Okay? And so the 0, what makes the denominator 0? Your MPV is your asymptote. Because your MPV was the original x-intercept. Okay? So looking at this graph, what's the MPV? X can't be what? positive 2. Notice that the asymptote for this graph, it's not the greatest graph here, but notice how the vertical asymptote is at x equals positive 2, because it'll never touch that. Okay, that's our asymptote here, because that's the MPV, that you can't divide by 0. Okay, notice the horizontal asymptote is what? Still, and always will be, y equals 0. Okay. So asymptote is a line that a curve approaches. I'm just going to highlight that. Let's not use green, let's use yellow. More and more closely, but never touches or crosses, okay? In Math 20, that's how we defined it. It's what we approaches, okay? The line x equals 2 is our vertical asymptote because that's the non-permissible value. That would make the denominator 0. The horizontal is y equals 0. And we are always going to do basic functions where that's the horizontal asymptote. You're not going to get a different horizontal asymptote in what we study in Math 20-1. Okay? So the vertical asymptote is always the x-intercept of the original function. So let's look at this function here. Okay, so how do we graph a reciprocal function? It's really helpful to graph the original equation. This is where grade 10 math comes in. So hopefully you paid attention in grade 10, especially in linear functions, where we drew graphs with mx plus b. So how do I plot y equals 2x plus 5 without my graphing calculator? Okay, 5 is the y-intercept. So we plot that. And then, what do I use next? Amog? Put that away, please. Thank you. Grade 10. Okay, we plotted the 5, the y-intercept. I'm trying to graph y equals 2x plus 5. Very basic linear equation. Yeah, I put you on the spot. It's kind of mean. But that's why you gotta pay attention. You're not even on the right page. Oh, man. Gosh. Now what? We're not answering A. We're actually just graphing 2x plus 5. Okay? Hey, 2 up, 1 to the right. See, you remember. You just got to be with us. Okay, so this is our slope of 2 over 1. Up to right 1. Down to left 1. I think you're going the other direction. Okay, so I don't know if you want to use a different color. Maybe you're graphing this one in pencil and your reciprocal you can do in pen. But you want to distinguish the two somehow. I'm going to make it blue. Daddy. Amog, I'm so proud of you. You paid attention a little bit in grade 10. Okay, so that's the function we're going to actually draw the reciprocal of. So we actually can use properties of this graph to help us draw the reciprocal without actually getting a table of values like we did last time. The first thing is we want to graph our vertical asymptote and horizontal asymptote. Easiest is horizontal. Where will the horizontal asymptote be every time? Y equals 0. So we want always do a dash line for an asymptote. I like highlighters. They're really helpful. Y equals 0. And where will the vertical asymptote be? Any guesses? Okay, well, let's answer A first, and then maybe you'll have an idea. What would be the reciprocal function? Y equals what? What would be the reciprocal of 2x plus 5? 1 over 2x plus 5. So we're graphing, we want to graph 1 over 2x plus 5. So you can think of your vertical asymptote also as your non-permissible value, or your x-intercept of the original function. What is the non-permissible value? What can't x be? Close. Negative 5 over 2, or negative 2.5, right? Look where your x-intercept is. Okay, the original x-intercept was where y is 0, and if you take the reciprocal of y equals 0, it's undefined. So your vertical asymptote will be at negative 2.5, where the x-intercept originally was. Okay, so there's my x equals negative 5 over 2. That's the equation of that vertical line. Okay, so we have two things. Now, when you take the reciprocal of a negative, it's still going to be negative. So negative 2 becomes negative 1/2, right? You're just flipping the number, you're not changing the sign. So, where it was below the x-axis, the graph is still going to be below the x-axis. Where it was above the x-axis, the reciprocal will be above the x-axis. Okay, so the next thing you want to plot is your invariant points. And those occur where y equals 1 and negative 1. So some teachers, what they'll do is they'll kind of like take a highlighter or something. I'll take a magic pen because it disappears. Okay, and I draw, okay, where is y equal to 1? And where is y equal to negative 1? Okay, at those points, that is where my invariant points are. Those are the points that are going to be the same when y is 1 and negative 1. So that would be right here and here. Okay, so those are the points that are not going to change. Like, look at my original function when y was 1 and when y was negative 1. Doesn't matter what x was. So what are the invariant points for funsies? Yes, I said funsies. Okay, so one of them was negative 2 and 1. And the other one's at negative 3 and negative 1. Okay, so when our y values are 1 and negative 1, those are our invariant points. Those are the points that are going to stay the same. Okay, from there, it's quite simple. It's easy to say that when you've done it many times. I already said where it's negative, it's going to become negative. We also talked about where it's getting larger, the reciprocal will get smaller. They're opposite reciprocals, right? So I'm going to draw the graphing. So it's going to approach 0 up here. Still negative, still below the x-axis. Because these ones are getting larger, these are going to get smaller. These are getting closer to 0. They're getting smaller, so now we're going to get larger numbers. Still negative numbers, larger negatives. Approaching the asymptote. Okay, there it is. Okay, on the other side, reciprocal of positive will still be positive. Let's move up a bit. Okay, so here, these numbers, these y values, are they small or big, these y values? These ones right here. They're less than 1. We call them small. So when we take the reciprocal of them, they're going to be big. They're going to approach that asymptote. They're going to be really large numbers. Okay. Notice where the original graph now gets larger, we're going to get smaller, closer to 0. So our red graph here is our reciprocal. So grab your graphing calculators. Let's double check our work. Okay. I thought I had a, oh well. Okay, so y equals, now this is a little bit trickier. When you're graphing this, you have to go 1 divided by, what do I need? Bracket 2x minus, was it plus 5? Oh, plus 5. Okay. And graph that. So some of you, did some of you get a vertical line here drawn at negative 2? The older versions? Draws in that asymptote? Like, looks like, yours might look like this. Like a heartbeat thing. Yeah, right? It's drawing in your asymptote, but shouldn't. is trying to connect these 2 points. It's just your asymptote. It's just the older versions. But this is what it looks like. Okay? So we'd actually call this point at x equals 2. So negative 5 over 2, negative 2.5. That's a point of discontinuity. So if you look at your table of values, go second graph. Okay, I'm going to change my settings here. Do you know how to change your settings on your table? No? It's second, yeah? Second graph for the table. Second graph. I'm going to go to second window for a second. And so what I want to do, okay, that's your table settings where you start, how much you go up by. I'm going to just change this to 0.5 for a second here. Okay? You can change it back to 1 later. The reason why is I want to show you something. Go back to your table, so second graph. Look at negative 2.5. That's where your asymptote is. Okay? That's your error. So, because it's only going up by 1s, it didn't show that. Okay? Yeah, it says error because that's an asymptote. Because you can't take the reciprocal of 0. Right? Okay. I just want to add something at the bottom. How do we solve for invariant points? So we found them here. They are when y is equal to what? Positive or negative 1. Okay, so if you want to solve algebraically, you can literally set y equal to 1. And it doesn't matter which equation you use because it's the same point on both equations. So it's easier to use which equation? 1 over 2x plus 5 or 2x plus 5? Probably just 2x plus 5. Okay? Because if they're the same point on both equations, it doesn't matter which one you use. Right? It's the point of intersection there. So you take your original, we can set the y's equal to 1 and negative 1 and solve for the x. That's how we algebraically determine the invariant points. So in the first one, I would subtract 5, which gives me negative 4. Divide by 2, and it gives you negative 2. So notice this point, x is negative 2, y is positive 1, right here. Subtract 5 is negative 6. Divide by 2, negative 3. So negative 3, negative 1. Here's your x, here's your y. Okay, here's your other point. So that if you need to algebraically solve for them, you could have used 1 over 2x plus 5 equals 1, and it'd give you the same thing in the end. Doesn't matter which equation, so why not just use the easier one? Okay, last page. Are you ready to try one on your own? No? Not at all? Can you start by graphing just y equals 3x minus 9 then? Okay, start by graphing that at least. You can do that. Okay? 1 over 3x minus 9. So we can see that our non-permissible value is the same thing as where our asymptote is, which is also where the original x-intercept was. We said x equals 3 is one of them, y equals 0. Those are the equations of the asymptotes. Okay. So you get that by taking your denominator, setting it to 0. Right? Where was the original x-intercept? Or you can think of it as a non-permissible value. Add 9, divide by 3. Right? Okay. So we want to graph this. Now, are these invariant points easy to kind of determine just by looking at them, the actual point itself? Not really. Could we plot it? Yes. How do I plot the invariant point? Where did the original graph, where what was equal to 1? X or y? Y. So where y was equal to 1, And when y was equal to, I'm going to zoom in. So where y is equal to 1, and where y is equal to what else? -1. So right there. Okay. How do I algebraically determine what those coordinates are? If I wanted to algebraically determine those points. Invariant. We take the original equation of 3x minus 9. We're going to set it equal to 1. And we also will set it equal to -1. Okay. So add 9 becomes 9. 10 equals 3x. Divide by 3. So 10, that's the same thing as 3.3 repeating. Does that look right for an x value? Oh no, I moved my graph. Does that look like 3.3 repeating to you? Right here, the x value. Yeah, it does. It does. So it's 10/3 and +1 is one of the invariant points. The other one is add 9, which gives you 8, and divide by 3. 8/3, right? Or what is 8/3 the same thing as? 2 and 2/3? Does that look like 2 and 2/3 for an x value? Yeah, it does. Okay. 2.6 repeating. So it would be x is 8/3, y is -1. Because we set y to -1 there. So those are 2 points. I'm going to zoom back out here. Okay, we're not done graphing it. Those are our invariant points. We need to actually graph this graph. Where it was positive, it's still going to be positive. So it's going to be in this area here because that's where the line was. It's going to be in this area here because that's where the line was. If I had a graph, just really quickly, say it was like this. Okay? Here's my asymptote. Here's my asymptote. My reciprocal would look something like this. Okay? Because wherever the original was, it's going to be in the same area. The reciprocal of it. If it was above the x-axis, it's still above the x-axis. And vice versa. Okay? If you had a negative slope. So here, did you already draw it in? Yes? Okay, sorry. So asymptote, approaching the asymptote. Approaching the asymptote. Asymptote. Okay? Do you need to plot those invariant points? If you want to plot other points, you can. So, for example, the point here of 4 and 3. When x was 4 and y was 3, what did it become? What would it become on for the reciprocal? 4 and we leave the x, we take the reciprocal of the y. 1/3. Okay, do you see how on 4 and 1, this is about 1/3, this point here. I didn't do the greatest at drawing, but the x stays the same. We just take the y value, take the reciprocal of it to plot it. Here, this would become, if this y is 6, and x is 5, becomes 5 and 1/6. Really close to 0. Okay, so that's what we're doing. All right, that's the end of this lesson. That's it. How is it? Yeah? Yeah, it takes practice. And so you want to practice. The assignment is page 403. And we'll practice more tomorrow. Tomorrow we actually look at, uh-oh, this all moved. There we go. Tomorrow we look at graphing quadratic reciprocals. Yay! 403 to 409. Numbers 1 to 5 AB, 7 and 12. Okay?